Okay, welcome. This lecture is going to be on GOT05, the topic of curved surface ray reflection. And this will round out our knowledge of geometrical optics. And the things that we want to answer in this lecture are: how do we construct a ray-based solution for curved surface reflection? And we'll work a fun example problem. We've already talked about how to trace rays through a medium and how to construct a field solution based on that ray using curvature. And of course, we all know from physics how to reflect a ray from a flat surface. Angle of incidence is equal to angle of reflection from Snell's law. But what if the surface is curved? So one of the things I hope you see in this lecture is how flexible and powerful geometrical optics is for dealing with things that are more complicated than just planar surfaces. So here's our basic problem. We're going to have a curved surface, and in 2 dimensions this is going to have 2 different radii of curvature. Remember, we defined Gaussian curvature in a previous lecture. You take 2 principal directions that are orthogonal to one another, 2 principal planes, and measure the radius of curvature. The Gaussian curvature is the 1 over the product of those radii. And we know that a wavefront also has a curvature. So at a given angle of incidence, you'll get a reflection. This is actually a very difficult problem because the relationship between the curvature of the reflected waveform and the curvatures of the incident waveform depends on a lot of factors. We've got angle of incidence, we've got the original curvatures striking the curved object, of course it depends on how curved the object is, so let's call that object curvature. And here we use rho subscript S1 and S2 to denote these 2 planes of curvature on the surface. And then another one is alignment. And that is the radii of curvature that you've used to define this incident wave may not even line up with how the surface is described at a particular point where the ray strikes. This means that the formulas get really, really complicated. However, if you make some approximations, for example, we know when we have a normal incidence and when the planes of wave curvature and the surface curvature are aligned. That is, if I drew a plane through the surface normal that was aligned with where I've measured PS1 and also PS2, PS2 would line up nicely with the radii of curvature and the surface normal that I've defined the incident wave. In other words, there's a plane that contains all of those vectors, both surface normals and the planes in which I've defined rho 2 and rho S2. And likewise, we've twisted the problem so that this radii of curvature aligns here. And at normal incidence, of course, we're coming straight down from above. So this is a simple case when we can describe the radii of curvature of the reflected wave as this simple formula: 1 over rho sub 1 prime, which is the curvature of the reflected wave, is equal to 1 over the curvature of the incident wave plus 2 over the curvature of the surface wave in the first plane. And likewise, the same formula holds for the other plane of curvature. Now, how do we construct our field solution? Well, we take the polarization along for the ride, aligning it as our incident wave. We can apply a reflection coefficient, like a Fresnel reflection coefficient. And of course, we have a phase factor from our standard ray optics solution. And then we take our Gaussian curvatures, our individual curvatures in the given directions, and we scale them by s, the distance. So s has units of meters, it's the length along the ray. This has units of 1 over meters. When you apply them together, you get a unitless value. The point s equals 0 tells you the field strength right at the reflection point. So we've defined the new ray solution where s equals 0 corresponds to the intersection point, and then incrementing s moves away from that reflection point. So it's an elegant little formula, and let's see if we can use it to solve an interesting problem. It's kind of a good historical problem. So, a receiver in North America is trying to intercept a clandestine transmission at wavelength lambda from somewhere in Asia by harvesting a portion of the radio signal scattered from the moon back to Earth. So we have Earth. There's a spot over here. It's going up. It's striking the moon. It's reflecting back to Earth, where the signal is being captured on the other side. So we have a distance traveled of approximately 380,000 kilometers. One way, and then reflecting back. And so we're going to make a ray optical solution that says if I emit at a certain effective isotropic radiated power, it's basically transmit power times gain of the antenna, how much do I receive back here on Earth? And we basically ignore rough surface scattering effects in this problem. We treat the moon as a giant orb, smooth on its surface. And we'll solve it symbolically so that we can see how to build up these formulas. Now, this problem actually has a very interesting history. In the early days of the Cold War, before Sputnik and subsequent other satellites were put into space, there wasn't any man-made satellites that you could use to spy on your adversaries on the other side of the world. So, before communication satellites and spy satellites were deployed, people looked at seriously trying to eavesdrop on one another by looking at the moon bounce. The U.S. actually had a research program back in the 50s that was dedicated to this mode of eavesdropping on the Soviet Union, trying to work out the math of how to get the radio waves off the moon and how much power you would need to listen to the transmissions. So basically just using Earth's natural satellite instead of man-made satellite to do your snooping. So to start this, I'm going to start with the link budget. Here's my EIRP, which is really just transmit power times my antenna gain, so it would have units of watts. Of course, the first free space equation says this is going to be wavelength in meters. This is the distance traveled on the first leg up to the moon. And what I'm going to do here is I'm going to solve this in terms of received power divided by antenna gain. And this is a trick in electromagnetics, because this is really proportional to the Poynting vector, or the watts per square meter, and is a nice measure of power, or power density. And the reason to see that is recall that my GR, my gain, is 4 pi, the effective electromagnetic aperture divided by lambda squared. So if I divide that into P sub r, what I basically get is a constant of proportionality, lambda squared over 4 pi, times what basically is the magnitude of the Poynting vector. So this is basically going to be proportional to E field or H field squared, which is why we like to work things in this particular form of the link budget. And we're going to assume that this is a perfectly conducting moon, or perfectly reflective moon that reflects all of the incident energy. It really isn't. The moon actually has a lot of propagation mechanisms that allow energy to penetrate its surface slightly and also roughly scatter in directions that geometrical optics wouldn't predict. But this is enough to get started and get a ballpark estimate and at least learn the behavior. So we know that we launch a spherical wave from the Earth. There's a point source over here, and the curvature, both rho 1 and rho 2, are going to be equal to the distance traveled by that spherical wave. So I'm going to have two identical terms, which in the previous solution there were two square rooted terms. Since we're dealing with power, which is proportional to magnitude of the field squared, I square those terms. So now instead of two square rooted terms that are identical, I have these squared. So the power that I receive at Earth is equal to the incident power, which I calculated up here, just from the basic free space equation. And then I alter the curvature with my new rho sub 1 prime, which we said was equal to rho sub 1 over rho sub 1 plus 2 over the curvature of the reflective surface, which in this case is the radius of the moon, 1,737 kilometers. Of course, if we want to work this in SI units, we have to convert that to meters. So don't forget to do that in all these examples. So when I plug that back in, this is what I get from the equation from the previous page. My incident energy proportional to field strength squared is now going to fall off by this kind of crazier amount. It will be a spherical wave still, We'll assume normal or near normal incidence in the problem. And when I plug this back into here, I get this final result. Where I fall off 1 over dm squared going to the moon, and then another 2 plus 2dm over rm quantity squared. Now, if I travel an appreciable distance from the moon, dm should be much larger than rm. In fact, it is in our problem. We said dm was like 380,000 kilometers. Which is much greater than rm, which is only 1,700 kilometers. So I can approximate this whole term here is really just 4dm squared over rm squared. So if I plug that back in, this is what my final result simplifies down to. The power that I receive on Earth is equal to the EIRP on the other side of the Earth times lambda squared times the moon radius squared divided by distance to the fourth. So it's a very lossy mode of propagation. And this constant of proportionality. Now, beneath this equation, I've put something from a completely different source. This is actually a form of the radar equation. This is for a monostatic radar. That is one that transmits and receives at the same location, goes a distance d sub m, strikes an object. We'll just draw an airplane. And then returns another d sub m to the receiver over here. And you'll notice that it has the exact same terms except for there's this radar cross-section term, sigma. This has units of meters squared, and it represents how big of an object something is to a radar. What's its area that it gathers energy and reflects back to it. The bigger the object and the more reflective it is, the higher the sigma. Now what's interesting about this is take a look. What does sigma have to be in order to match the result that we just derived from geometrical optics? Well, in order to get the equation to work, sigma should be pi r squared, the area of a circle that has the same radius of the moon. This should be a really gratifying result, because if we have a sphere with radius rm and it's a good reflector, when I shine radiation upon it and reflect back, the cross-sectional area, pi r squared, is what gathers and then re-emits signal back to Earth. So that closes the loop between what we know about radar and our geometrical optics result to show how we handled that curved result correctly. And before we go any further, let's do a little thought experiment here. Remember, on the ray-based solution, we put a ray to that point, and then we reflected it back to Earth. Here's the moon. And really, we just used local information right there about the radii of curvature. In this case, it was r sub m to the center of the moon. Interestingly, only information at this local point was used to solve the problem, but we got the intuitive result that was the cross-sectional area of the entire moon that reflected information, signals and information and power back to the Earth. So it's interesting that this local piece of information really tells you the extent of the size of something. Knowing something here tells you the result here. So let's do a quick thought experiment. What if I had an undulating moon, an amoeba moon? Would I still be able to use geometrical optics on this? Well, the answer is probably. If my ray came down here and struck this surface, I would now have a much tighter radii of curvature. The ray that reflected back would have a far smaller amount of power density than the ray that I constructed over on the smooth moon example. However, I would now have multiple rays that would satisfy angle of incidence equals to angle of reflection at a particular location on Earth. So interestingly, as the surface gets curvier, I have smaller contributions from each little curve, but I have more of them that superimpose constructively and destructively. But if you averaged out over space all those results, you would find that roughly you'd get the same result. The individual weaker reflections, but more of them, would combine to give you an average power that would be approximately pi r squared of this mass. So that's an interesting thought experiment. It kind of shows how the optics result transitions you into more complicated phenomenon. And even though we're just using localized information at the reflection point to calculate the ray behavior, such as curvature, that behavior is necessarily linked to other properties, global properties of the entire object that we're using to study. So this pretty much concludes our geometrical optics analysis for this phase of the course. So GEO, as we like to call it, is of course a ray tracing and using ray methods. We'll be transitioning into another technique, which is best described as PO, or physical optics. And this is using radiation theory to project radiation using techniques that are much more akin to wave mechanics. And the first lecture that deals with this is the uniqueness theorem that we reviewed last week when I was on campus. Now, we're going to do things in a particular order because it turns out that when geometrical optics degrades, you can correct some of the behavior, particularly at sharp interfaces, using something called the geometrical theory of diffraction. And we'll actually use a physical optics result to illustrate how we get one of those geometrical theory of diffraction correction factors. And in fact, there are corrections to physical optics that involve something called the physical theory of diffraction. And there are further corrections that can be made using something called the uniform theory of diffraction. So that gives us a roadmap of some of the tools that we're going to build in our arsenal for handling analytic electromagnetic problems. We'll be building this out over the next several weeks. And finally, when we're done, we'll have a really good toolbox for all the different analytical methods for studying EMAG problems. And we'll find some shortcomings, and we'll basically develop a theory of surface scattering that will help fill in those gaps. And then we'll also deal with random problems, adding stochastics, random rough surfaces, or other features of scatterers to solve more difficult problems that have uncertainty to them or ill-characterized behaviors. So that's the general roadmap for the rest of the lecture series. And you should all be 7th level wave masters by the end of the course.